So thank you for coming back. We have our first guest talk, which is from Christine Tass from Knexus Research. And online, we have Gary Howarth from NIST. And they are going to have a pretty interactive session. She has promised me I get to throw the cube. So I'm super excited for their talk. The name of their talk is Underpinning Problems in DP, and just take it away.
Okay, sounds good. So actually, we're going to start with Gary. Do you want to unmute?
Yeah. Okay. Can you hear me?
We're good.
Great. All right. Thanks very much. I can't see the slides, but I'll trust that there are some up. Let
Everybody
me.
here can see them. Um, Hopefully, they're visible online.
They share screen. They are.
Yeah.
They are.
I can see them.
Yeah.
Here. Why can't I then? There we go. Okay. Got it. Brilliant. All right. So, thanks very much for this invitation and opportunity to speak. The community meeting last year was one of the most valuable meetings that I attended, and I'm sad that I'm not able to join you in person. But I'm happy to talk a little bit today about some of the work that we're doing at NIST to try and support privacy enhancing technologies in general and differential privacy specifically. And then I'll turn it over to Christine to go through sort of what will be an exciting interactive session of topics that we think will intersect well with the work that NIST is doing to support. So first, I mean, for those of you that don't know, the National Institute of Standards and Technology is a U.S. government agency within the Department of Commerce. Actually, will you go back one slide? Sorry. So thanks, Christine. And so the NIST is an agency within the Department of Commerce. And I'll draw your attention that the Department of Commerce's seal, it features a lighthouse quite prominently. And I like that lighthouses are the quintessential public safety technology. They support safe passage and promote trade for all without discriminating against any. And this is similar to the vision that I hold for NIST's role in supporting privacy enhancing technologies and differential privacy. I think that we can build tools and frameworks and networks that are going to support the entire community, and that's for the greater good of everyone, I think. Um, so let's go on to the next slide. Thanks. So NIST seeks to facilitate organizations and individuals deriving benefit from. So I want to talk a little bit about why and how NIST is supporting privacy research. One is um, we are encouraging the effective management of risks. So we have a number of tools for looking at risks for privacy and for artificial intelligence, and a number of other topics. This is one of the key strategies for NIST in general, is helping organizations navigate trade-offs. NIST is known as a world leader in measuring and in metrology. We'd like to bring that expertise to privacy. Since we don't have a regulatory function and we don't have any commercial interests, we're neutral ground. And that means that we are a great place to hold benchmarks that can serve the entire community. And finally, NIST is a research library. It is an institution that maintains the standards for the United States. And that means that we're a perfect place to contain use case analysis. All right, next slide. So we have four pillars that I envision as supporting any sort of PETS decision. So any privacy enhancing technology decisions that organizations are making, I think going to have at least four major components that they're going to have to consider. We're going to have to consider the trade-offs between metrology, the risk assessment, benchmarks, and the use case analysis. I'm going to give a brief example of how we're supporting the development of these four different areas and domains on the next slide. Specifically, we have a program called the Collaborative Research Cycle that is trying to support the foundation for synthetic data and de-identification technologies. It's a massive benchmarking exercise where we have released some data, some benchmarks that we call the diverse community excerpts, and we ask the public to de-identify them. So we've gotten about 500 de-identified instances covering dozens of sets of distinct algorithms, many of which are differentially private. And so we packaged all these into a giant archive. That archive is accompanied by a whole set of metrics on every single de-identified instance. So that's our metrology piece. We have this package we use called SD-NIST that has dozens of different fidelity, utility, and privacy metrics. And over the next year, we're planning on beefing up the privacy metrology to incorporate many additional empirical privacy evaluations. We're working with organizations right now to try and document specific use cases that they have for synthetic data and try to map that to risk assessment tools that we have. And then we can have how are organizations navigating these complex sets of choices between what their organization needs, desires, what their duties are, and then what they're actually going to release in the end. And so these types of questions are going to be essential for organizations to ask if they're going to navigate for them, for a specific use case. What's epsilon mean? And then why this epsilon for this specific use case? On the next slide, let me give you a specific example that might motivate this before I turn it over to Christine. These are some data that are drawn from the collaborative research cycle. On the left, you see an example of one of the metrics that we have in SD-NIST. This is a regression analysis that uses education to predict income. So on the x-axis, we have the educational attainment from 0, which is none, to 12, which is having a terminal degree. And then the income decile is the binning of earners. The top data is the original data distribution. And then the bottom is some synthetic data that have been produced. And you can see that the synthetic data have a slightly skewed distribution compared to the original data. On the right, I'm mapping the error for a specific set of algorithms using different values of epsilon. So as the epsilon decreases, you can see that the error in the bins increases. This is, of course, obvious. I think everyone would understand this, that as the epsilon decreases, the utility is going to decrease. And what I want to draw your attention to, though, is that these differences for a specific epsilon, they affect different subpopulations within the data, different rates. So that's to say that the utility and privacy trade-off for individuals isn't the same across the entire data set. It's going to be dependent on that specific subset and demographic groups. And this is going to be an important thing for organizations to consider when they are looking at specific use cases and when they are trying to think about data releases and other applications. So organizations are going to have to ask about in their risk assessment, not just what's the risk of releasing the data to the organization or to the individuals, but what's also the risk of releasing poor quality data? What are the risks of having effects on specific subpopulations that are more detrimental than to other subpopulations? And this risk is going to be heightened in synthetic data applications where there may be important downstream consequences. So I hope that this sort of shows you some of the programs that we're working on. You could collaborate with us in the collaborative research cycle. You could just type in collaborative research cycle and you can figure out lots more about the program. But now, let me turn this over to my collaborator, Christine Task from Knexus Research. And so she's going to explore some of these specific issues in an exciting, interactive session. So take it away.
Thank you, Gary. Okay, so we'll just start with this. I've talked to a lot of people about what I'm about to present over the past few weeks. Could you raise your hand if I have talked to you in the past few weeks, or in a lot of cases, the past 24 hours, about the concepts in this talk? It should be all of Joe's students. All right. So if I haven't talked to you yet, you're going to get to see some new stuff. If I have talked to you, thank you very much for the ideas you suggested that hopefully you'll see represented in here. Nobody's seen the slides, so it's all my fault if this looks dumb. All right. How many people saw the other NIST talk, Naomi Lefkowitz's talk at TPDP? Did you notice that bit where she said, maybe we're never going to get epsilon figured out? So I think we might be able to get epsilon figured out. And this is the, in what Gary showed you and the work that I do, we sit in between the data, models, a large selection of models and techniques and attempts to make synthetic data, and the stakeholders who are coming to us with real significant concerns about how this is going to impact the output and how that's going to impact all the decisions, policy, everything else that gets based on the output. So that's the bullet that goes with this one. This is a source of frustration and concern and discussions that have kind of motivated what sort of things do we need to resolve to actually make progress on epsilon, how to set epsilon that's going to resolve the concerns of the stakeholders. Another time to raise your hands. How many people in here have published a paper or done any other work with a differentially private algorithm where the point where you were getting reasonable utility was at an epsilon greater than 3, or with a privacy definition that was weaker than add or remove all information associated with one individual? So if you've done social network stuff with edge privacy, if you have done, events data and you made assumptions, add or minus just one event, so everybody, right? So we are all together in this idea that there must be some definition of effective privacy that we're okay with that's not strictly what's being mandated by the epsilon differential privacy definition. Relationship to you. So a recommendation of conversation I had yesterday. Some of this is presented as recommendations to paper reviewers, suggestions to paper reviewers, and suggestions to researchers. You can see if you agree with me or not. I'm identifying 4 underpinning problems that I think we haven't looked at a lot, that we can look at relatively easily. Some of these are going to be themes you've heard echoing because we're all running into it over the past 3 days. But there's things we can do right now that will help. And if we do it, we start to get much closer to not what is epsilon, but what should we set epsilon. Structural error is error that doesn't vary with epsilon. By the way, there are quizzes, so pay attention. It is error that doesn't vary with epsilon, especially patterns of error that are fundamentally dissimilar to uniform random sampling error. This is things that, because of the way we've designed our algorithm, we're going to be making the same mistake on the data every single time. Why is it hard? So what this really is, we have to deal with this. It is one source of error in our outputs, and it comes from machine learning statistics. They also have these problems. All modeling of human data has these problems. They're not resolved yet, but we're having to confront them, these sources of bias, because we make them worse. When we start tuning our models, in order to reduce the sensitivity, in order to look at the data as little as we have to be able to run our queries and do our output, we are picking parts of the data to ignore. And so there's the question of, are we ignoring the parts that are okay to ignore, right? And how does it relate to epsilon? So it impacts performance independent of epsilon. So if I'm coming to and all of my use cases are going to start with synthetic data, but I would like to invite contributions from you guys in your areas of expertise, because I suspect these occur everywhere. But in synthetic data, if there is a dependency between, let's say, gender and your second focus, like in the differential privacy survey you took, that marginal was not released, that wasn't collected. We've lost that dependency if that dependency existed. And so every time I run that, if I base synthetic data on that marginal, I'm going to lose it. That's going to be a structural bias in my output. If somebody comes and they says, I want to do, regression on gender, that's going to be information we don't have. If there's a dependency there, we'll get into that. Other sources. So folks working with machine learning. models that are doing, classifications, predictions, recommender systems. Have you thought about where structural error gets introduced into your approaches? Anyone? All right, Sharon, you got to be quick on the thing. All right. So we'll do this. It's a good thing to think about. If you haven't thought about it, here is something that you can do right now in a straightforward way on your next paper. So, and this is kind of suggested by what Gary showed you for an example there. So how many of you have heard the term disaggregation? That's basically probably how much you hang out with government data or statisticians. Thank you, Gillian. That is, Gillian is one of the statisticians I hang out with. And we should have this debate about naming and terminology, but disaggregation, which is a term, there's a White House guidance that came out recently, and it's basically the idea of when you are releasing data, when you are doing evaluations, don't just do the evaluation for the whole population, break it into subpopulations, especially subpopulations that we expect to have, substantially different distributions. You can start out by, let's see error by gender, let's see error by gender and race. But maybe you know something interesting about your data. Maybe the people from this geography or this income bracket are very different than this other bracket. These types of users and those types of users, right? Release error separately, and you'll start to see how your algorithm is treating different parts of the data distribution. And you can check. So, we don't tend to like to go up to epsilon of 10's already a little crazy, right? People don't generally go, but go above 10. Do one evaluation that runs epsilon all the way up so you can see just in whatever error you were, check you were already doing, how much of that is coming from the randomness and privacy and how much of that is coming from the way you built your algorithm to try to touch the data as little as possible. Okay? When you're doing reviews, real easy. If you're in statistics, government stuff, you're already being asked to do this. Just look for some disaggregated reviews, evaluations. Ask people to do disaggregated evaluations. All right. Underpinning 2, data-dependent breaking points. Properties do you maybe quietly expect your data to have? When you're writing an algorithm, are you thinking like, it's got about this many columns and this many rows? Everything's secretly categorical. There's no numbers, so we can bin it all very nicely, which is a great thing for marginal methods. We're making assumptions that all of our class predictions that we want to do, have at least a certain amount of representation, that nobody's clicking only on one link every hour, every day for a full year. Like, what assumptions are you making about your data? And what happens when your data doesn't satisfy those assumptions, right? So we all look at how performance degrades as we decrease epsilon. Another thing that we can look at is how performance degrades when we change the properties of the data that we're pretty sure are going to impact performance. And this is necessary. So previous thing, necessary for identifying bias. This is necessary for reproducibility and generalizability. If you only do evaluations on 2 data sets, I have no idea if it's going to work for mine. And okay, that's great. If we can get an agency to pay Knexus or Tumult or somebody to spend 6 months tuning an algorithm for them on their data and discovering what doesn't work and iterating and whatever. But if you guys can do some work initially, looking at just real simply the assumptions of your data, as you change them, at what point does your algorithm die, right? If I just randomly subset the rows and I try running on half the rows or a quarter of the rows, at what point does my performance fail? Then that gives me a clue of whether I can use your algorithm or not on this new data set. Great thing for science, reproducibility and generalizability. And this helps us determine whether we can solve someone's use case at a level of protection that they're willing to accept. And this is the same problem. So with the OpenDP survey, there was a lot of things we would have liked to release. Show you guys, we managed to pick some interesting ones, but with an epsilon of 2, because the data was so small, And because of the way marginals, and histograms depend on the number of individuals per subclass and the dependencies between the features, 3 was all we could get. Right? Okay, so I assume this is going to go as well as the last one. How many of you have thought about where the data breaking points are for your algorithms and in your research area? Good. Some good hands to see it in the back. I would love to see all the students and coworkers of the people that just raised their hands. So, all right. I assume all of these have breaking points. Reproducibility check. When you're doing a review, look to see in the experiments section if the evaluations are checking performance with respect to data set size or data set properties, right? Have they only evaluated on one data set? Have they seen, you just take that same data set, you don't have to do 50 data sets, take that same data set, but degrade the quality of that data set. Just reduce the size, increase the columns, decrease the columns, whatever makes sense for your application. All right, 3. This is the popular one. Nobody's going to argue with this one. I think I heard this a lot this past week. Characterization of, do this real quick. So note whether we can solve someone's use case for an epsilon value or level of protection that they're willing to accept. What if what they'd really like is kind of a high epsilon? What if we're past 2, past 3, starting to get good utility at like 5 or 6? We could have told you all the marginals in the world for like a utility of 6 or a epsilon of 6, right? From that survey. So that's when we have to, we weaken the definition. Everybody here does it, or we use, weaker parameters. And then what would be really good to see is underneath that section that occurs in all of our papers that says this is the definition of privacy. And it's got sometimes very quietly the definition of what the, how you're defining adjacent worlds, sometimes only in italics and math, just a sentence of plain English. We're going to say the worlds vary by 1 week of data. So this is going to provide privacy. You can go farther. Just say that sentence and we'll be doing better. But you can go farther. You can say privacy is going to degrade for, like this, for users who have the same week of data, every week or something for extreme outliers, right? So nice thing is we're just providing some intuition. You can say, okay, I think from my privacy definition, this is what's going to happen for Bob, who only clicks on that link. This is going to what happens in the pathological case and characterize what protection they've got. Can also characterize when we're thinking about privacy metrics or empirical privacy, what's the requisite knowledge? So in synthetic data, what that looks, well, we'll get to that in the next slide. But what this does is this lets us think through the implications of a higher epsilon value. So rather than picking it and saying, oh, it looks fine, the utility is kind of still terrible at epsilon 3, probably the privacy is fine at epsilon 3, or whatever approximate thing we've been doing so far, this lets us start to think through it. So in synthetic data, if I looked at the characterization of privacy protection, that's unit privacy, we generally do add and remove one whole record because we can, we've got some reasonable number of columns. Attack, I want to know if I can infer, whether you were infected, whether you were disgruntled with your employer, something like that, with higher confidence if you participated in the data than if you didn't participate in the data, right? So, and that means that now I can, I've learned something about an individual person from the data. That's one type of attack. There's membership inference, there's reconstruction, and so on. Knowledge complexity. So actually say intuitively, what is the knowledge complexity I'm assuming here? I'm assuming that the attacker knows the values of K columns precisely for a superset of the rows. So they have like some outside data source. So that's some people who are in the data, some people who are not in the data. They're trying to learn about the people who are in the data. There's variations of that, right? Here we're getting to privacy metrics. I can do this by empirical checks. Maybe I could do it by entropy approximations. We'll keep moving. All right. These exist everywhere else, right? So we've got privacy metrics. That's a whole other genre of work. Merging the two a little bit. is basically a matter of saying intuitively, what are we doing with our privacy definition? So just that, just the very simplest thing. There's a long pathway of research here, but the very simplest thing, reviewers, when you're looking at the privacy definition, do they have any intuitive sense underneath that? You can request that they add one, right? Some example. If they can add metrics, that's great too. Okay, finally, let's quickly consider a different unambiguously mature technology category. So NIST has overseen lighthouses. NIST has overseen the meter stick. NIST has overseen the automobile, nuclear arms, and power plants. Gary and I spent a few weeks just sort of trading strange articles NIST had written. In the 1910s, they were concerned about the flammability of curtains in theaters. They've considered a lot of things, right? Automobiles. We know what happens. Okay, she got an automobile. An automobile is an object. It interacts with the world. It has some defined physics rules. It has some things we need to worry about for safety. One of the things that we need to think about, very important anytime we're looking at an automobile and safety, is how it interacts with the road conditions. If the road is slick, if the road is at a certain incline or decline, right? So this is where we've got special rules for giant trucks going down hills, and we have to have special lanes of traffic for them. So you have the object that you're engineering, and you have the conditions that it's running in. We don't know what happens when we put an algorithm on data. So one of the ways that not only us, but all of machine learning is less mature fundamentally than automotive engineering is because we know a lot about our object, some reason about our object. We know much less about the thing that we're putting it on and what happens when the two interact. We don't have nice abstractions for data. So I talked a little bit about the factors in data that affect tabular data, synthetic data. We talked a little bit about sources of structural error, talked a little bit about thinking about privacy and characterizing it. That ends up being a lot to think about, right? But here's the neat trick. When they figured out the math for automotive engineering, is anybody here besides me ever heard a lecture on finite elemental analysis? It's the best thing. Okay, cool. Great. So you take the car and you make it into a lot of tiny triangles, like a simplex, like a computer graphics algorithm. And you can model the physics between each of those nodes, right? So now I've got think like a computer graphics type model. And then I can much more simply in a computer, discrete, interacts, the physics as it interacts with its environment, right? But they didn't have to do that for all possible objects. They did it for cars and trucks and bikes. And so one thing that we can do is streamline our use cases, right? So in order to make progress on all this stuff, rather than trying to solve the entire world, we can refine on some things we know are important, have high demand, and then we know something about. We've got synthetic data. There's social network-based recommender systems, summary statistics for evidence-based policy. This is things like Tumult's work in education statistics. There are things like classification models for automated decision-making. All of these, if we can nail them down in such a way that we can talk about their data abstraction, qualities of the data that make them break, sources of structural error, privacy requirements, objective thing that we're trying to get out of it, then we start to being able to actually mature the problem, actually get through the workload that machine learning has left us with. So proposed advice for reviewers. Consider the valuable contributions of papers that don't create new algorithms. How many, just out of curiosity, I've got no idea. By the way, this is the best, that we did a very private survey and I'm doing a very unprivate survey here. But how many folks had research that they had a poster or something like that, or a talk or a 5-minute thing? In any of this period, TPDP or OpenDP? People have, it's okay. Okay, batch of people. Of those people, how many of you were introducing a new algorithm or defining a new problem versus investigating something on an algorithm and a problem that already exists? How many people are doing new stuff? How many people are the paper, there was a previous paper, and you're doing a refinement on that paper. Cool. All right, so that's some good hands. I'm happy to see that. Consider the valuable contributions of things like that. Don't create new algorithms or define new problems, but instead revisit existing algorithms to identify sources of structural error, like bias, data-dependent breaking points, implications, and limitations of privacy definitions. Because those are how we get to having cars on roads. All right, I think I foreshadowed this parenthetically at the beginning. Why can we sometimes get away with bigger epsilon? So I have a hypothesis, and this is part of why my underpinning problems are what they are. At epsilon 10, creating synthetic data with a noisy histogram, by noisy histogram, I mean, if I've got 4 features, my histogram has all 4 features in it, and I'm taking counts of people who, have property A for feature 1, property B for feature 2, and so on. I'm exactly capturing the data set. And let's say Bob is unique in the data set. Bob is the only person that has those 4 properties. At epsilon 10, creating synthetic data with a noisy histogram does anybody know? It will exactly reproduce its initial input data. So if I'm taking a noisy histogram, all I do is add Laplacian noise to the counts. If a count is 1, and I add Laplacian noise from a Laplacian distribution with a scale of 1/10, I don't add very much noise at all. That goes from a count of 1 to a count of 1.001. All the unique people in the original data are exactly still there in the synthetic data. It looks exactly the same. But in the NIST CRC, we run a lot of algorithms at epsilon 10. That is one of the most common epsilons we use. We do 1, 5, and 10. So why would we do 10 if 10 provides no privacy? And 10 is not guaranteeing privacy at all. The 2 neighboring worlds can be thousands of times apart in terms of relative probability. But how many of you are familiar with the probabilistic graphical model for synthetic data? So basically what we're doing is we're capturing conditional probabilities. So I've got feature A, age, sex, race, something like that. I'm grabbing the conditional dependencies between them. If this guy right here, if these 2 are independent of each other, I don't need to collect them because they're going to come out independent anyways when my model gets done generating data. So I use this to generate data by saying, okay, given a value of A, I can, with my pairwise conditional probability, I can say, given A, what's the most likely value for B? Given A, what's the most likely value for C? Now I have a value for A, B, and C. I've got a record. That performs well on empirical privacy metrics, especially as you add more features. So the more of those, I'm going to select A and B, then A and C, then B and D, and so on, the better we see it perform with respect to empirical privacy. Why can we sometimes get away with bigger epsilon? They also do great on utility, by the way. Like they actually do better than the histograms on utility. Come up and ask me if you want to know why. Proposition. For a given data, with a given set of abstract properties and breaking points, if we can introduce more entropy into our algorithm without introducing structural error, we will get good utility and better empirical privacy for the same epsilon. So the simple explanation, you can tell me if you believe me this or not, but the simple explanation here is I rolled the die once here, a very small amount. I rolled the die a lot of times here, right? There's much more entropy in this algorithm. There's much more opportunity for the data to wander from its original distribution. But I'm still getting good performance for all the things I care about for synthetic data, if in fact the data has pairwise dependencies where these 2 are dependent, these 2 are dependent, and these 2 are independent. I'm not introducing structural error. The error that I will get will look like a sampling error. Okay, so algorithms, these things exist in the wild, probably, right? Algorithms that appear to provide good utility and good empirical privacy across a wide range of data conditions, even at a higher epsilon, have probably found a way to do it, even if they're not explicitly thinking about structural error, even if they are not thinking about their data abstraction, even if they haven't found data, breaking points, even if they're not thinking about likely attacks, they have probably trial and error or whichever intuition led them, reached a point where they are performing well, right? They're solving these problems. They have lots of entropy without introducing structural error. So it's an interesting question. What abstraction are they implicitly using? Where did they break? Can we find them further? Okay, wrapping up. So I've already said this out loud, but here it is just as a quick reminder. What can you do to help? Real simple, and these are small things that you can throw into papers you're already writing just in the evaluations. Do some disaggregated evaluations. The government folks will love you for that anyways. We're all supposed to be doing it. Just evaluate on subgroups, just to see, so that's documented. Consider subsampling or capping to make sure your subgroups are relatively evenly sized. And by the way, the disparity that Gary showed between Asian men and white men, Asian women and white men, we also see disparity in that data between white men and white women. So these performance differences is not just the population size, it's also the population size, but it's not only the population size. There's actually interesting things about the distribution, where the car hits the road, what conditions the road has. So just do disaggregated evaluations. And this helps us track source of bias. Also, if you think you can get away with it, because it's fun and interesting, see how you do with like a very high epsilon, right? Set epsilon to 100 and see what happens, just so you know. Data-dependent breaking points. What might break your algorithm? Think about it. The simplest, lowest, most accessible fruit. It's so easy to do this. Just do your evaluations while you're doing the one with epsilon. Pick your favorite value of epsilon and see what happens if you just take an 80% subsample, uniform random subsample of the records in your data, and a 60% uniform random subsample of the data, and a 40% random subsample. Just see what happens as you reduce the number of records in your data and see at what point it breaks. That'll be the very first thing that I need to know if I want to find out if I can deploy your approach on a data set. But you can also look at the amount of information per record and synthetic data. You can look at changing the number of columns. You can look at how you subsample or clip individuals, events per individual, if you're looking at event data. Lots of things you can go look at. Okay, this will help with reproducibility, generalization, adoption, deployment. And also, I think it's going to be fun. I think it's going to have some neat opportunities for further research to push these boundaries. You've been hearing this all 2 weeks, so I won't spend a lot of time on this. I'm just going to say one important thing. Don't be afraid of saying we're not going to protect an outlier who looks like this. Because in reality, people are already doing things on data that's sensitive. They've been releasing sensitive data forever. Statistical organizations have been doing this forever. They already clip extreme outliers. Like, worst case scenario, we'll just drop those people. We'll fix it somehow, right? If you don't need to have them. But say something about your privacy definition, because if you don't, we don't have any understanding of the limitations of your privacy protection. We don't understand how to configure the algorithms, and it's difficult to grow the market for the tools we're making. Streamlined use cases. So all the folks that had a paper where they found an existing one, they found a way to improve it. That's really cool. That's fun. More of that we get, the closer we're going to get to where we want to be. And that's it. Okay. So epilogue thoughts. If you have any criticism or suggestions, I'm sure some folks do, or ideas or thoughts or whatever, please come bug me. They will go into the next version of this. There's going to be a next version of this. So the Eyes Off Data Symposium in Dublin next month. Jack, if he hasn't retracted the offer, I'll be doing this again there. Please check out, if you just search for NIST CRC, you will find some benchmark data that we have curated to cause headaches for anybody who runs on tabular survey data. It includes Native American reservations in Oklahoma. It includes HBCU neighborhoods in the South. It has Chinatown in San Francisco. It's got area around University of Michigan. It has very diverse, very interesting, strange, creative distributions that break algorithms. So please come play. We have pictures. You can see a stop sign in Cherokee. Okay. And thank you very much. Everyone helped. We have shadows have offended. You can forget the whole thing, right? But this is my rant. Thank you very much for having time to do it.
So Gary, if you're still online, and Christine, maybe have 3 minutes for questions if anyone would like to ask the question. Come on, guys, I really want to throw this.
No, stunned silence is what I aim for here. It really is fine. If anybody has any thoughts or questions, please come up and talk to me. If you want to yell at me for not accurately representing your ideas when we've discussed this previously, come do that too. And always iteratively improving these observations. Thank you.